Download this code from codegive.com, link in the description below. Cache memory, direct mapping, a comprehensive tutorial with code example. This tutorial will delve deep into the concept of direct mapped cache memory, a fundamental technique in computer architecture for improving performance by exploiting locality of reference. We'll cover the following. 1. Introduction to cache memory * why we need it and the basic principles. 2. Locality of reference * spatial and temporal locality, the foundation of cache effectiveness. 3. Cache memory organization * tag, index, and block offset. 4. Direct mapping explained * the mapping scheme, address decomposition, and the mechanics of cache hits and misses. 5. Direct mapping algorithm, detailed step-by-step process of searching, updating, and handling conflicts. 6. Code example, C++ a practical implementation to simulate a direct mapped cache. 7. Advantages and disadvantages of direct mapping * weighing the pros and cons. 8. Performance considerations * factors affecting cache performance. 9. Beyond direct mapping * brief overview of other cache mapping techniques, associative and set associative. 10. Conclusion * summary and key takeaways. 1. Introduction to cache memory. Modern CPUs are significantly faster than main memory, RAM. This disparity in speed creates a bottleneck. Every time the CPU needs data, it must wait for RAM to respond, slowing down overall execution. Cache memory is a smaller, faster type of memory that sits between the CPU and main memory. Its purpose is to hold frequently accessed data, allowing the CPU to retrieve this data much faster than accessing RAM. Think of it as a short-term memory for the CPU. Key concepts ****. Cache hit * when the data requested by the CPU is found in the cache. Cache miss * when the data requested by the CPU is not found in the cache, and the CPU must access main memory to retrieve it. This results in a performance penalty. Cache line / block * the unit of data transferred between main memory and the cache. Typically, a cache line holds several bytes. Address translation * mapping a main memory address to a cache location. 2. Locality of reference. The effectiveness of cache memory relies on the principle of locality of reference, which states that memory accesses tend to cluster in time and space. There are two main types. Temporal locality * if a data item is accessed, it is likely to be accessed again in the near future. This is common in loops and accessing frequently used variables. Spatial locality * if a data item is accessed, nearby data items are likely to be accessed in the near future. This is common when accessing elements of an array or sequential instructions in a program. Cache memory exploits these principles by storing recently accessed data and nearby data, anticipating that the CPU will need them again soon. 3. Cache memory organization, tag, index, and block offset. To understand how a cache maps main memory addresses, we need to break down the address into three components. Tag * identifies the specific block in main memory that is currently stored in the cache line. Index * specifies the particular cache line, or set of cache lines, where the data might be stored. In direct mapping, the index directly points to a specific cache line. Block offset * indicates the position of the desired byte within the cache line, or block. The number of bits allocated to each component depends on the size of the cache, the block size, and the total addressable memory. Example ***. Let's say we have address space *32-bit, meaning we can address 2 to the power of 32nd bytes of memory. Cache size *1 KB, 1024 bytes. Asterisk block size asterisk 32 bytes. Here's how the address bits would be divided. 1 block offset asterisk since the block size is 32 bytes, 2 to the power of 5th, we need 5 bits for the block offset. This allows us to select any of the 32 bytes within a block. 2 number of cache lines asterisk the cache has 1024 bytes, and each block is 32 bytes, so we have 1024/32 equals 32 cache lines. 3 index asterisk since there are 32 cache lines, 2 to the power of 5th, we need 5 bits for the index. This allows us to uniquely identify any of the 32 cache lines. 4 tag asterisk the remaining bits are used for the tag. In this case, 32, total bits, 5, index, 5, block offset, equals 22 bits for the tag. Visual representation asterisk. 4 direct mapping explained. Direct mapping is the simplest cache mapping technique. Each block in main memory has a fixed location in the cache where it can be stored. This location is determined by the index bits of the memory address. How it works asterisk. 1 address decomposition asterisk the CPU generates a memory address. This address is then broken down into the tag, index, and block offset, as explained above. 2 cache lookup asterisk the index is used to locate the specific cache line that might contain the data. 3 tag comparison asterisk the tag stored in that cache line is compared to the tag from the memory address. 4 hit or miss asterisk. Asterisk cache hit asterisk if the tags match, it's a cache hit. The data is found in the cache at the specified offset within the block. Asterisk cache miss asterisk if the tags don't match, or the cache line is marked as invalid, empty, it's a cache miss. The data must be fetched from main memory. 5 cache update, on a miss when a cache miss occurs. Asterisk the entire block containing the requested data is fetched from main memory and loaded into the cache line specified by the index. Asterisk the tag for that cache line is updated with the tag from the memory address. Asterisk the requested data, identified by the block offset, is then returned to the CPU. Analogy asterisk. Imagine a set of numbered mailboxes, the cache lines. Each mailbox has a small space for a name label, the tag. When you have a letter for someone, you use their address, the index, to find a specific mailbox. You check the name label on the mailbox to see if it's the person you're looking for, tag comparison. If it is, you take the letter, cache hit. If not, cache miss, you have to go to the post office, main memory, to get the letter, then put the letter into the mailbox and write the recipient's name on the label, updating the cache. Conflict misses asterisk. A major drawback of direct mapping is the potential for conflict misses. If 2 different memory locations map to the same cache line, i.e., have the same index, they will constantly replace each other in the cache, even if there's plenty of other empty space in the cache. This is also known as thrashing. 5 direct mapping algorithm, detailed. Here's a detailed algorithmic representation of how direct mapping works. Explanation asterisk. 1 address decomposition asterisk the address is split into block offset, index, and tag using bitwise operations. The AND operator performs a bitwise and is the right shift operator. 2 cache lookup asterisk the index is used to directly access the corresponding cache line in the cache array. 3 tag comparison asterisk the valid flag is checked to ensure the cache line contains valid data. Then, the tag in the cache line is compared with the extracted tag from the memory address. 4 cache hit/miss asterisk based on the tag comparison and valid bit, the function determines if it's a cache hit or miss. 5. Cache update, on a miss. If it's a miss, the function simulates fetching the data from main memory. In a real system, this would involve reading from RAM. It then updates the cache line with the new tag and data, and sets the valid flag to true. 6. Data return *. Whether a hit or miss, the function copies the requested data to the data read array. In a real system, the CPU would access this data. 6. Code example, C++. Here's a complete C++ code example that implements a direct mapped cache. How to compile and run *. 1. Save *. Save the code as a .cpp file, example direct_mapped_cache.cpp. 2. Compile *. Use a C++ compiler, like G++, to compile the code. 3. Run *. Execute the compiled program. The code will simulate the memory accesses and print whether each access results in a cache hit or miss, along with the first few bytes of the data read and a snapshot of the cache state. This allows you to see how the cache is being updated and how hits and misses occur. 7. Advantages and disadvantages of direct mapping. Advantages *. Simple implementation *. The mapping scheme is very straightforward, making it easy to implement in hardware. Low cost *. The hardware required for direct mapping is relatively inexpensive. Fast hit time *. Since there's only one possible location for a given memory block, the tag comparison is quick. Disadvantages *. High conflict miss rate *. This is the most significant drawback. If two or more frequently accessed blocks map to the same cache line, they will continually displace each other, leading to poor performance. Poor performance in certain scenarios. Direct mapping struggles with applications that have access patterns that repeatedly access memory locations that map to the same cache line. 8. Performance considerations. The performance of a direct mapped cache, and any cache, is heavily influenced by cache size. Larger caches generally have lower miss rates because they can hold more data. However, larger caches also cost more and may have slightly longer access times. Block size. Larger block sizes can take advantage of spatial locality, but they can also lead to increased miss penalty if the entire block is not used. Smaller block sizes reduce the miss penalty but may not effectively exploit spatial locality. Programs access pattern. The way a program accesses memory has a huge impact. Programs with good locality of reference will benefit greatly from caching. Programs with random access patterns will see little benefit. Replacement policy. On a miss, direct mapping has an implicit replacement policy. The new block always replaces the existing block in the assigned cache line. More complex caches, like set associative caches, have explicit replacement policies, example least recently used, LRU, to choose which block to replace. 9. Beyond direct mapping, associative and set associative caches. Direct mapping is the simplest type of cache, but its limitations have led to the development of more sophisticated techniques. Fully associative cache. A block from main memory can be placed in any location in the cache. This eliminates conflict misses but requires complex and expensive hardware to search the entire cache in parallel. Set associative cache. A compromise between direct mapping and fully associative. The cache is divided into sets, and each set contains a small number of cache lines, example 2-way set associative, 4-way set associative. A block from main memory can be placed in any line within its assigned set. The index bits determine the set, and the tag is used to distinguish blocks within the set. Set associative caches provide better performance than direct mapping at a reasonable cost. 10. Conclusion. Direct mapped caches are a fundamental concept in computer architecture. They are simple to implement and offer a significant performance improvement over accessing main memory directly for programs that exhibit good locality of reference. However, they are prone to conflict misses, making them less effective for applications with less predictable access patterns. Understanding the principles of direct mapping is crucial for comprehending more advanced cache designs like set associative caches, which strive to balance performance, cost, and complexity. This tutorial provided a comprehensive overview of direct mapping, covering the underlying principles, address decomposition, the cache hit/miss process, a code example, and the advantages and disadvantages. Experimenting with the code example and varying the access patterns will help you solidify your understanding of this important topic.